Hey, manufacturing world, welcome to another episode of Shop Matters, sponsored by Okuma America. I'm your host, Wade Anderson. Joining me in the studio today is David Fisher. Welcome, David.
Thanks for having me.
All right. So, David, introduce yourself. Tell us a little bit about you.
Yeah, David Fisher, lathe product specialist. I handle the turning centers, and been at Okuma for quite a while now. I'll be 30 years come September, so a bit of a high watermark there for me.
Yeah.
It's been great. I started off in the applications engineering department. Was in there for almost 20 years, and then moved over to technical support for sales. So in this position, everything from working on the machines to product management in applications, and now technical support for sales.
Okay. So I started with the company in 2005. So you've been there a lot longer than I have, about twice as long, I think. So I started years ago, and I've said this on a couple of podcasts, I think, but the very first chip I ever cut was on an LB15.
Right.
I used to work for Whole
Great
Set.
machine.
Yeah. I worked for Whole Set Turbo down in Charleston at the time. And they had cells. They had two LB15s, and then they had a horizontal machining center. And so that was my first experience. I came from the fab world. I programmed Amada and Salvagnini shears and press and brake systems. So the first chip I ever cut was a LB15 Okuma, and now fast forward all these years later, I work for the company. But I remember when I first started, I knew what the LB15 was, and that was it. I really didn't know much of the product breadth. And you get involved with it, and you got LUs and LTs and Genos lathes, and back then there was ESLs and Multis, and there's all these different models. What do kind of talk us through what the different models are? So if people out there are listening and they're familiar with an LU and not an LB, or vice versa, they know an LB and they've never heard of an LT. What are these models, and what differentiates them?
Okay, well, so basically we break it down into vertical and horizontals, and then we've got our turning centers and our multitasking centers. So for the horizontal market, we'll break that down further into the number of saddles. So when you talk about your LB15, that's our premium, which is now an LB3000, by the way, but that's our premium single saddle machine, and you can get that turning only, milling, Y-axis, subspindle. You can basically take it up to what would be, right on the threshold of becoming a multitasking machine, right? So you can do a part complete, start to finish. When you move to the LUs, now we're getting to two saddles. So with the LU, we have an upper and lower saddle. They can work independently, or they can work in a synchronized fashion. So if you want to do pinch turning, which would allow you to add a measure of chatter suppression, because your two tools are supporting each other, right, and supporting the part. That's takes you to a higher level of production, particularly for shaft work and that type of thing. And then we move up to like the LT, which we can have two or three saddles, matching spindles. Excuse me. And they're all milling capable. You can put Y-axis on all three. A very high production type machine for very complex parts. Then we'd step up to multitasking, which would be our Multis product line. Okay. And we kind of do the same thing on verticals. We go to a vertical. We have the LBEX is our kind of our bread and butter horizontal turning machine, whereas our 1SP-EX, VEX, is our bread and butter vertical turning machine, right? Boxway construction, super rigid, great for production. And we go all the way up to multitasking machines with our VTMYB, which is almost like a vertical Multis platform, so to speak.
Okay. Taking a Multis multifunction machine, standing it up, basically.
Yeah.
Okay.
Can't get a subspindle, but.
Yep. Yeah, and you can't bar feed it.
Right.
So out of the product line, do you have a favorite? Do you have one that you just tend to gravitate to, that you like running better than others?
Yeah, I mean, the Multis is just one of those types of machines that you're only limited by your creativity. It's just a lot of fun to take that in different and unexpected directions. I mean, it can do a lot of things. It kind of got started as a a market for in the market for high end shops that have high capability, but then it's like, okay, well, let's turn this around. This is a great quick change machine, right? So for
Right.
job shops, you don't want to invest a lot in fixturing, rotary tables, and all that kind of thing. With the Multis, that's all built into the platform, right? So all that setup, all those extra machines, your investment setup time is minimal, and I can go from part to part to part very quickly. And having been in production, I worked in a production shop for 18 years before I came to Okuma. And it was just setup time was just a major headache, right?
Right.
Because we spent hours. We didn't have many CNC machines. When that setup time goes to single minutes, 5 minutes, 10 minutes setup time, all of a sudden that stress of, oh, we got a hot job, you got to tear this down and set up another job. You may have to tear down 3 machines,
Yeah.
that problem goes away, right? Because you're just talking minutes, so who cares? Let's set up the next job. We can send the finished parts on the previous job to the stock room, and we'll get back on it when we finish up here. So
Yeah.
it's the Multis is really great. But at the same time, I want to throw out here about the LBEX. That's just such a heritage machine, right? Which I call a heritage machine. It's been around for so long. It's evolved to such a high pinnacle of accuracy, thermal stability. I mean, it's truly an amazing machine. So that's got a special place in my heart as well.
Okay. So lead me through, and I don't know, was there a predecessor to the LB15? Was there a model prior to that we would have seen in the States?
Well, the LB15 was sort of the, Okuma's been around for over 100 years, right? So
Well, yeah, aside from the
been
manual
the noodle
things.
machines, right?
Yeah.
But the LB15 was sort of a watershed moment for Okuma, right? So that kind of set Okuma on the map as a premium machine tool builder.
So you just mentioned something that might be interesting. I think a lot of people will know this, but some won't. But how Okuma actually got started in manufacturing. Aichi Okuma decided that he wasn't happy with the thickness and consistency of the noodles and started making noodle making machines, and went from designing the dies to roll the noodles to realizing the equipment that he was using to roll the dies wasn't of good enough quality. So he got involved in actually manufacturing everything to make the entire noodle making machine, which led him to need metal cutting equipment to be able to cut the gears and turn shafts and things of that nature. And we got our first patent in 1914 for a manual lathe that hit production in 1918. And then, you kind of fast forward to the United States, and my first introduction with Okuma was the LB15, the CNC lathe. And my father and I had a uncle that worked at Eaton's in Shenandoah, Iowa, and they kind of revolutionized their manufacturing process back in the day, from going from vintage World War II type manual lathes to a CNC lathe, and it was the Okuma LBs that they loaded the shop full of, back when they first kind of turned on the CNC world. So just a little quick injection of some history on Okuma. So
Okuma's been around for a long time. So and you wouldn't think accuracy was all that important with making noodles. I guess is kind of what I'm thinking. How accurate does a noodle have to be? But evidently it has to be pretty accurate. So.
Right. So the LB15, what has changed as you go through the different generations from like a 15 to an LB300 to an LB3000? What were some of the technological advances as we went through those machine model changes?
Yeah, I mean, real quick, more power, more torque are two things just right off the top. But probably the biggest thing, and I think something that's really appreciated by our customers, is the design of the machine that has made it more thermally stable, more thermally predictable, and then you add our technology on top of that with the LBEX series. We added TAS, which is our thermal active stabilizer system, and that's software that controls the size of the machine as the machine heats up or cools down. So now your operator doesn't have to be involved with constantly adjusting offsets. And even more important, when you put it in a automated cell, right? So you just want that to run. And, you've got minimal thermal growth from when you come in on Monday morning. Everything's cooled down, and you start to run that cell and it warms up, but that size really stays stable.
Right.
So that's been a big change. Okuma also introduced our Prex motors, which are on our milling motors and most of our spindle motors, which is a magnetic segment switching motor instead of a coil switching motor. Very, very efficient. So the motor can produce the same output, but still be smaller, or be smaller, excuse me.
Okay.
And it so therefore you've got less issues with balance. You can accel and decel faster because your moment of inertia is less because the rotor is smaller. So really, when you have motors in a confined space, right, that really makes a difference. It also generates less heat. So again, going back to that whole thermal stability question,
Right.
now we're putting less heat into the system through our motors, right? So.
I think that's a big talking point. I know I've touched on mills a lot. It's a easy thing for me to talk through, like a Genos M560 for an example. But on the lathes as well, we spend a lot of time engineering out all the heat sources that we can. So talk a little bit about the plane, if you will. So if I remember right, the LB15s, the headstocks basically were mounted flat, but then I think your headstock and your tailstock were both flat, but then your turret was mounted at an angle. So as things heated up, things were growing apart from each other.
Correct.
How does that change from then to now?
Yeah, so, and you can see this evolution as we went. So we had the LB15, just as you said, coolant in the casting.
Yeah.
Right? Different planes for the different machine components. We went the LB15 Mark II, coolant, we moved that out of the casting, and we put everything on the same plane. So a 30-degree slant bed, and of course the turret's mounted that way, but then we set the tailstock and the headstock mounting to be 30 degrees as well. So now when everything grows, it's growing in the same direction. And I mean, there's nothing you can do to not have growth. I mean, heat, it's physics, right? So, so that was the Mark II. Then we went to the LB300. Well, that's when we went to our box slant bed design. So basically, it's a two-piece design. The guideway system, along with the mounting of the tailstock and headstock, is one casting. And it goes on Okuma's philosophy of simple shapes. So in order to make this growth that's going to happen predictable, we need the shapes to be as simple as possible. So it's, again, it makes it easy to predict. So there's no shape that you're going to use in a machine tool simpler than a cube. Right.
Yep.
So we create that guideway system, the mounting, headstock mounting, tailstock mounting. That is a cube. And then we put that on a 30-degree base to give us the chip evacuation ergonomics advantages of a slant bed lathe. Right? So we get the best of both worlds through that.
So you're basically building it like a flatbed lathe, and you're using the base like a sign plate to stand it up and get that 30-degree benefit that you're looking for.
Yeah. And again, if you go back to the old flatbed lathes, I mean, they're very thermally stable, right? So we've kind of reached back to the past and are using that with our current machine because that is the best solution.
Yep.
Right. So
It coming from a grinding background, if you ever look at like the sub-micron grinders, super precision grinders, Saki grinders, they make one. Strauzak used to make one. But if you look at those, all the motion system of those grinders is exactly what you're talking about. It's on a rectangle, separate base part, and there's isolation pads from the bed, I should say, to the base. And they do that, again, to control thermal stability and growth. And then having that closed box, you've got a very rigid system, and then everything's mounted on the same plane. So I looked at that, when I first started working at Okuma, coming from a grinder background. As soon as I saw that LB, it's the first thing that popped in my head is, wow, they're building this just like these sub-micron grinders, separating the motion system from a platform that the largest piece of cast iron has a lot of angles and cutouts, and areas for chip conveyors and things like that. It's more prone to the environment than the actual motion system.
Right.
So yeah, very interesting.
Yeah.
So let's spend a little bit of time. I'd really like to know more about technologies that Okuma's got on their turning centers that maybe people don't hear enough about or know enough about. So whether it's standard stuff on the control or just optional content that exists that people should be aware of. So I'm going to kind of lob some out there and have you kind of step me through some of it. So let's start a big one, and I might have touched on this on a previous podcast a year or so ago, but I led a tour at Japan many years ago. We went to the headquarters in Oguchi, and in the auditorium, I asked how many people in the audience have Okuma lathes. Like 80% of everybody in the audience raised their hand. And I said, okay, out of everybody that has Okuma lathes, how many know about harmonic spindle speed control? And like all but 2 hands went down. And I thought, wow, that was a little bit of an eye opener for me, that out of an audience this big, only 2 people in the crowd even knew what harmonic spindle speed control was. So step me through a little bit on what harmonic spindle speed control is, if it's standard and things like that.
Yeah, and that really is surprising because it is a standard feature. So obviously we need to get the word out there better. But so what harmonic spindle speed control does is, or what it is, it's a function that will help you manage chatter, vibration in the machine. Mm-hmm. So a lot of your chatter is created by harmonic buildup in the part. Mm-hmm. And so you first start cutting and you're fine, but then there's harmonics build, and they amplify each other, right? So, and then you get chatter, you get vibration, get chatter. So what harmonic spindle speed control does is let us pick a variation in RPM by percentage. Mm-hmm. So, I typically, when I use it, I start off at 30%. That just seems to be a good number, base number to start with for me. But, and then you have the period of variation. So how quickly do you want that RPM to change? And then there is a third option to let you plateau at the top and bottom of that RPM. So what happens is, and we do that basically to minimize striping, because you are changing the RPM. So you are changing the cutting conditions, right?
Right.
And when you do that, it can create a change in your surface finish, right? So what we do is rather than come up to that peak RPM and then down instantly, we plateau there and then come down off of that, and that helps minimize any kind of striping that you might get because of that.
Okay.
But it's entirely programmable. Once you come up with the numbers that work well for a given part, you can put those parameters in the program. Mm-hmm. The next time you run that part, you're all set to go. No need to adjust it. You're off and running. So we can go to a longer length to diameter ratio when we're turning parts than we could without that feature.
Okay. And that's one of the things that I saw it used most on is, for that case exactly, is length to diameter ratio. Mm-hmm. In a perfect world, you want the perfect setup and you want everything correct where you wouldn't have the ability to induce chatter. Reality, though, is there's times where there's geometries you have to do it. You have to get a length to diameter ratio beyond what you would want or is recommended.
Right.
And this is a tool to, can help assist you through some of those kind of challenges.
Without having to go to the added expense of a steady rest. And, that introduces issues as well. So,
yep.
Yeah.
Okay. How about torque skip?
Yeah, torque skip, again, it's another feature that's standard on linear axes on Okuma machines. Mm. And so, we can measure the load on our axes. And so with torque skip, it's typically thought of as when we're passing off a part from main to sub spindle. We bring the sub spindle up. We want to put some pressure on this part, make sure it's seated. We monitor that. We have, the pressure we want to go to comes up, touches the part, goes to that load, and then it knows to go to the next step, which is typically clamp with the sub spindle, unclamp with the main spindle, go back, and you're off and running. Mm-hmm. But we can use it in far more creative ways than that. So, for example, we had a part where we were doing introducing sawed-off billets to the machine. And I'll just say that they were less than precise. Okay, so we had some variation in length. We were doing a center drill in the end. We had to make sure that we had a proper center drill, right? So we wanted enough taper for the center. We didn't want to get up on the barrel of the center drill, or we would lose contact with that taper. So we had to find that end. So basically, we came in with the turret. We had a dummy tool, right, just to push on that part, and we used torque skips. So we came up, moved in, touched that part, went to our preset load. We knew we had the end of the part, captured that value. So now we knew the Z position. And then we could set our center drill to drill the proper depth.
Okay.
We could also use it to check to make sure the part wasn't, well, they didn't load the improper part, right? It's too long, too short. Or if just the person doing the cutting, if they miscut a part and got it too long or too short, it would alarm out. No sense going into production on a part that's going to be scrap or, needed to be modified.
Right.
So yeah, a lot of different ways to use it. We also have an option available for C-axis torque, and what C-axis is our spindle. So we've actually used that to find a feature on a part, right? So if you have a machine that has milling, we can go in there, find where a boss is, without having to use a gauging system, right? So casting.
Kind of clock the part.
Right.
Okay.
Yeah, it's not like we have to be within a thou, but we need to know where that boss is. We can check both sides, do a stock divide, come in there and hit that boss right in the middle. So
okay, and you touched on it, but some of the operations that you would do with a gauging cycle using a part probe, things like that. If you've got a machine that doesn't have gauging or a part probe, you can actually use torque skip to kind of get creative and find some of those features that way.
Right. And like I said, except again, C-axis is option, but everything else is standard. So, it's on the machine. Make use of it. Right?
Yeah. So tell me a little bit about Peck Turning. I know this is something you did some testing on recently on one of our LUs in the partners building. Talk me through kind of what that process is and where would it be beneficial for customers?
Yeah. So Peck Turning is a fairly new function, and it's primarily for dealing with stringy materials. And we have customers that really struggle to get some of their difficult to machine materials under control for automation.
Okay.
And then, of course, any customer that works with plastic, that's built-in stringers, right? So, so what this does is this lets me set a given amount of feed and then a given amount of dwell. So I can set the feed in 50 thou and then dwell for, typically I don't want, if I'm cutting steel or anything like a metal, I don't want to dwell on that surface for too long, right? So I want to actually get back into the cut before I've done a full revolution. So I can set that time delay, the dwell, to allow me to do that, right? So I'm gonna move in 50 thou, I'm gonna dwell 3/4 of a revolution, and then I'm gonna move 50 thou. Typically, from what I've seen, that's enough to break the chip of anything short of plastic. Plastic, you don't really care if it's sitting on the part so much, so you can let that dwell go a little longer. Make sure you break that chip. But so for example, I had a part I was cutting when I didn't use step feed function. That chip did not break from the start of that cut to the end. I was cutting about 175 millimeters, I think. My chip was 60 meters long.
Wow.
Right. So you just ended up with this wad of chips around the part, around the chuck, and you had to dig your way out, right?
Right.
So we added this function, and we set it to a 2 millimeter step. We kind of play around with 2, 1.5. So we ended up with a chip that was basically half a meter long, which still is a pretty long chip, but it's a spiral, so it kind of surprised me it was a half a meter long when I stretched it out. But it created an environment where the chips did not wrap around the part. The main thing, right? And we used 2 millimeters. We occasionally would get one that would hang up, a single chip. But I'm like, okay, if that's if we're doing a manual load operation, the operator can just knock that chip off, no big deal. If we're doing auto load, we'd probably go more like 1.5 millimeters, which we didn't have any chip wrap at that point. right? So you can play around with the parameters. Again, you can put it in the program. So once you've come up with what works, save it in the program, you're done. That's good for the future.
Okay. So
but
you
yeah,
just recall it through a
Right.
G code or?
Oh, no. It's basically the program. It's a line in the code. When you hit cycle start, it'll load those parameters
Oh, okay.
for that function. And it'll cut that way. So yeah, that's one of the powers of OSP that's really amazing. All these parameters to these functions, you just load them in the program. Once you have everything figured out, and then from then on out, it's just plug in the program and off you go.
Yeah.
So
All right. What about help me on the term ZW overlap function?
yeah.
Okay.
So this is a function. It's used on a subspindle machine.
Right.
Okay.
Which for us is our W axis.
Correct.
Okay.
Correct. And so, obviously you've got one turret, you've got two spindles. So, you're cutting on one side, you finish there, then you typically will go over and cut on the other side or transfer the part on the other side. With ZW overlap function, it allows us to have a tool in both directions and program both spindles, and the turret will adjust for that.
Okay.
So for instance, if we're drilling main and sub spindle, and maybe I'm feeding it 12th thou on the main spindle, and I'm feeding it 10th thou on the sub spindle. Well, the turret's going to move in at 12th thou on the main spindle. The sub spindle is going to move in at 22th thou because it's got a comp for the 12th thou that I'm moving in, that the turret's moving for the main spindle,
Right.
and then do the 10th thou feed. So, quite often, or most often, that's going to be used for ID work, drills, that type of thing, because we've only got one x-axis.
Right.
But I have seen it used in high production situations. A subspindle machine. It was actually on our Genos product. They used a double turning tool, and they used the offset to control one, and then they had a adjustment on the subspindle side. So they had symmetrical parts. They basically had the same, both ends had the same features, right?
Okay.
Drill, tap, turn, and chamfer. And they had this special, adjustable turning tool. They turned and chamfered the OD at the same time. They drilled at the same time. They tapped at the same time. They're done.
Wow.
So yeah, very high production, very efficient use of their machine.
That's a great way to reduce a lot of cycle time out of your part.
Yeah, definitely.
Okay. So on twin turret machines, so like a LU or an LT, talk through some of the functions on how you can basically mirror up between two turrets.
Yeah, so something that's unique to Okuma for multi-spindle, multi-turret machines is we program everything as if it's upper turret, left spindle.
Okay.
And then we use G13, G14 to flip it upper to lower, and G140, G141 to go main to sub spindle.
Okay.
So it's really nice in that if you decide to reprocess the part, you program it for the upper turret. Now you want to do that machining from the lower turret. You don't have to reprogram it at all, change your radiuses or anything like that. You just put a G14 in front of it, and now it's run on the lower turret. So it makes it very, very easy to handle. Also, in my years of experience, I've always thought of Z negative into the part, Z positive moving clear of the part.
Right.
In our process, that's true no matter what spindle you're on.
Okay.
Right. So anytime I see a Z negative, I'm thinking into the part. So very nice feature that way. And then with multiple turrets, we can run independent or we can run synchronized. So like for our LT, we have two turrets, two spindles. I may have one turret on each spindle for most of the time, but the side that takes the longest time to produce, I may want to jump over there with both turrets for a period of time to balance my cycle time. So we have synchronization codes. We call them P codes. We can synchronize the program when we need to, and then run independent when we don't need to.
Okay.
So for things like pinch turning, like we were talking about before, where we're balance cutting, cutting with the two tools. We can sync that up perfectly, eliminate chatter. Again, go to a longer length to diameter ratio.
Okay. So one last one, A/B synchronization. Tell us what that is.
That's basically a mirroring function. So you can program the upper turret and then tell the lower turret to do what the upper turret's doing.
Okay.
So my favorite example for this is grooving. If I have 4 grooves to cut apart, I'm gonna program 2 of them for the upper turret. I'm gonna shift the lower turret off to cut between the grooves that the upper turret's doing, and just tell it to mirror what the upper turret's doing.
Okay.
So, and again, the more grooves, the better, because I'm going to program half the grooves, and the other one's just going to follow what I tell it, the upper turret, to do. So any changes, I make it to the upper turret, and they're automatically incorporated in the lower turret. So again, it's a mirroring function. It's one of those things where you can get as creative as you want to get with it. But you'll want symmetrical features on a part, basically, is when I see that, I'm thinking, okay, I can use this function.
Okay. Excellent. Well, David, thank you for joining us today. I really appreciate it.
Oh, my pleasure. My pleasure.
And thank you for joining us. If you have any thoughts, ideas, questions about this podcast or ideas for future podcasts, please feel free to reach out to me. You can find me on LinkedIn. And be sure to check out all of Okuma's social media sites for additional videos and other machine content. Till next time, we'll see you then.